Hello everyone. In our previous video of AC circuits, we had started various terms related to alternating waveform. Again, in this video, we are going to start another terms related to alternating waveform. In our previous videos, we had discussed what is cycle, what is frequency, what is peak value, what is angular frequency, and many other terms. So here we are going to discuss few another terms related to alternating quantity. So let's start with the first term related to alternating quantity, and that is average value. So first of all, what is average value? Average value that can be expressed by a DC quantity which transfer the same amount of charge to the any circuit for a particular time period, which can be transferred by the alternating quantity in that same circuit in that same time period. So that DC parameter can be defined as the average value for an alternating quantity. Here we can calculate the average value of an alternating quantity by two ways. First method is known as a graphical method, and next one will be analytical method. So here we have one waveform of an alternating quantity in which we have shown one cycle of an alternating quantity, and for that one cycle we need to find out the average value of this alternating waveform. Now first of all, if we calculate the average value of this full cycle, then what will happen? Here in this waveform, if we observe the positive cycle and this negative cycle, so both are identical, just they have different polarity. So if we just directly calculate the average of this full cycle, then that is going to be 0. So that's why when we will have a symmetrical alternating waveform, we cannot find out its average value of a full cycle. That is always going to be 0. That's why whenever we are going to find out the average value of any alternating quantity when it is symmetrical waveform, then we will always prefer half cycle. So here we are going to find out the average value of this half positive cycle. So basically, how we can find out the average value? Basically, we are going to consider the all instantaneous value which are on this positive half cycle, and just we will find out the average of those instantaneous value which are on this positive half cycle. But practically, it is impossible to consider all instantaneous value which are on positive half cycle. Why? Because they are going to be in infinite numbers. So instead of that, you can do one more thing. Let's suppose this positive half cycle which is on 180-degree time period. We are dividing that angle or that time period into n numbers, in n equal parts, and basically we are considering those instantaneous value which are on this considered point. Here in this diagram, we have divided that waveform or that positive cycle into 10 numbers, and we had considered those 10 points over this positive cycle, and on those 10 points we had considered their instantaneous value as shown in this diagram, that are V1, V2, V3 up to V10. So basically up to now we had 10 instantaneous value at same interval on that positive cycle, and in graphical method we will just consider these 10 values and we will find out the average of those 10 values, and that will define the average value for that positive cycle. So that is mathematically given over here in this equation. Here the average voltage V average is equal to V1 plus V2 plus V3 up to V10 divided by total number of those instantaneous value, that are 10, so divide by 10. So this formula will provide the average value of that positive cycle. Here we have another method by which we can calculate the average value, and that is analytical method. And for that, we are again consider same sinusoidal waveform over here. In analytical method, we are going to find out the average value using integration method. And for that, again we will consider half positive cycle. And when we integrate, when we apply integration in any function, what is the output or what is the result of that integration? That provides the area under that curve. That means if I am going to integrate the function of this half positive cycle, that will give result in form of the area which is under that curve. And here if we need to find out the average value of that curve, means average height of that curve, so that can be calculated by dividing that area by its base length. That means if we are integrating this waveform or equation of this waveform up to from 0 to pi, then that integration will provide the area under that curve which is under 0 to pi, and base length for that positive cycle, that is from 0 to pi, so that is pi. So if we will divide that area by pi, so that will provide the average value for that waveform. So let's start the integration over here. Average value, that is the integration of a particular area divided by base length of that waveform. So that is mentioned over here in this first equation. Now let's put the value of that function. Here we have a sinusoidal function, and we know the mathematical form of that waveform, that is Vm sin omega t. So if we just put the value Vm sin omega t in this integration, and we are going to integrate it in between 0 to pi. So we are consider limits 0 to pi, and as well as that's why we are considering base value pi minus 0 means pi, that is in division over here. And if we consider this value which is in integration portion, here Vm is a constant. Here we are going to integrate this term sin omega t with respect to theta, that is nothing but a omega t term. So when we will integrate this term sin omega t term, that will provide minus cos theta, means minus cos omega t term. So if we just put the value minus cos omega t term over here with that limit 0 to pi, and again if we just put the limit in that equation, so first term will be cos pi and next term will be cos 0, and we know that what is the value of cos pi, that is minus 1, and what is the value of cos 0, that is plus 1. So first term will be minus 1, second that is minus into plus 1, that is again minus 1 basically. So minus 1 and minus 1, that will provide minus 2. But again here before this at the starting of this equation we had a minus sign. So minus over here and minus in this bracket will cancel out each other, and that's why we will have a final term, and that is 2 into Vm divided by pi. And if we find out the value of this 2 by pi, that will provide the value 0.637 into Vm. So this is the final value of average of this sinusoidal function. So this is the method how we can calculate the average value of a sinusoidal waveform. Now we are going to start next term, and that is RMS value. So here let's start the RMS value. First of all, what is RMS value? First of all, full form of RMS, that is root mean square. Now how to define RMS? RMS value of an alternating quantity is equal to the DC value which when flowing through the given circuit for given time period, it produces the same amount of heat which is produced by the alternating current when it is provided to same circuit for same time period. So that equivalent DC current or DC voltage will define the RMS value for AC voltage or AC current. Now again here we are going to calculate the RMS value for this sinusoidal voltage. Again, how to calculate RMS value? As its name indicates, that is root mean square. So basically what we will do over here, we will consider the mathematical function of that given waveform. First of all, we will find out the square of that function. Next, we will find out the mean of that squared value, and lastly we will find out the root of that result, and that will provide the RMS value of any alternating waveform. And for that, again, let's consider that we are going to find out the RMS value for this positive half cycle. So again, as we had done in previous topic, we had considered 10 instantaneous values at same interval of time, and that are V1, V2, V3 up to V10. And we are going to calculate the RMS value based on this instantaneous value. And as I mentioned, first of all, we will find out the square of these values V1, V2 up to V10. So that's why in this equation here we are considering graphical method, and based on that we are calculating the RMS value. So that's why first of all we will find out the squared value, and that are given over here. Here we are consider V1 square, V2 square up to V10 square. And next we will find out the mean value of this squared instantaneous value, and that is again done in this given equation over here. To find out the mean value, we have done V1 square plus V2 square plus V3 square up to V10 square, and that is divided by total number of values, and that is 10 in our case over here. So this equation, again, if we find out the root value of this term, that will give the RMS value for this given waveform. So again, lastly we have done the root. So this value which is given in this equation is the equation for RMS value for this given waveform. So this was the graphical method. Again, we can use analytical method to find out the RMS value. And for that, again we will consider same diagram over here, and again we will consider same positive half cycle. And again, if we calculate the RMS value based on analytical method, so first of all, based on its whatever its name indicate, we will find out the square value. Again, we will find out the mean of that, and lastly we will find out the root of that. So first of all, we have a function and mathematical formula that for that function, that is Vm sine omega t. So first of all, we will find out the square value of that function. So that is Vm square sine square omega t. And to find out the mean value of that squared function, we will put that function into integration. But now you can consider half or full cycle. In both ways you can calculate the RMS value. Why? Because we have done this square over here, and when we have done the square, if value will be positive, then square of that is going to be positive. If value is going to be negative, but again square of that value is going to be positive again. So here there is no chance to become the value 0. That's why you can use both limits, 0 to pi or 0 to 2 pi. So here we have considered 0 to 2 pi. Now based on this consideration, let's find out the mean value by integration, and for that, here we are finding the integration of Vm square sine square omega t in limit of 0 to 2 pi, and we will again divide that integration portion by the base length, that is 0 to 2 pi. So 2 pi minus 0, that is again 2 pi. And lastly we will find out the under root of that function. That's why this equation is in under root. And if we find out the integration, but before that we cannot find out the integration of sine square omega t directly. That's why instead of sine square omega t, we just replace the term 1 minus cos 2 omega t divided by 2. Here we have a 2 constant in this integration, Vm, and divided by 2. So that is separated over here. And if you find out the integration of 1 minus cos 2 omega t, then integration of 1, that is going to be theta means omega t, because this is with respect to omega t means theta. And integration of cos omega t, sorry, cos 2 omega t, that is going to be sin 2 omega t. But 2 which is in multiplication with omega t, that is going to be in division over here. So finally we have term omega t minus sin 2 omega t divided by 2, and we will apply limits on these both terms. And if we put the limits on first value omega t, that is 2 pi and 0, so that will provide 2 pi minus 0 means 2 pi. Now similarly, if we apply this value 2 pi and 0 in this function, so sin 4 pi, this will provide sin 4 pi over here, and we know that sin 4 pi is 0. Similarly, if you put 0 into this limit, so sin 0 again, that is again 0. So both value for this term is going to be 0, which is mentioned over here. So in bracket, we have value that is 2 pi minus 0. And here we have 2 pi, and in division we have 4 pi. So that will cancel out each other, and we will get 1 by 2 over here. And lastly, if you find out the under root of this given equation, so on upper side, that is Vm square, so we will just have Vm, and division means we have 1 upon 2 term, and if we find out the under root of that term, so that will provide the 1 upon under root 2. So finally we have an equation, and that is Vm by root 2, and 1 upon root 2, that is the 0.707 into Vm. This is the final value of this RMS value. So this is the method how we can calculate the RMS value for an alternating waveform. Now next term, and that is peak factor or amplitude factor or crest factor. What is that? The ratio of the maximum value to the RMS value, that is peak factor, that is given over here, maximum value by RMS value. And if we just put the value, let's say previously we had defined the maximum as well as the RMS value for voltage, and that let's say maximum value for voltage, that is Vm, and RMS value, that is 0.707 into Vm. So that will provide the 1.41. So peak factor for a sinusoidal waveform, that is 1.41. Similarly, in next term, and that is form factor. What is the form factor? It is the ratio of RMS value to average value. Again, in our previous topic, we had derived the RMS value as well as the average value. If we just put those values over here, as an example, RMS value, that is 0.707 Vm, and average value, that is 0.632 Vm. So we will have a value that is 1.11, which is given over here. So this is the value of an form factor for any sinusoidal alternating waveform. So this was all for today's lecture. Thank you for watching this video. In our next video, we will start the phasor representation of an alternating quantity.